Good evening. I'm Jim Beatty. I'm the chair of the Ohio State Department of Physics, and on behalf of our department and the university, I'd like to welcome you to the 51st Annual Smith Lecture. This lecture is held once a year and is intended to bring distinguished scientists to Columbus and to Ohio State to present their insights of subjects of general interest to the campus and Columbus community. The lecture is a tribute to the memory of Alpheus W. Smith, a former Ohio State professor, former chair of the department, dean of the graduate school, and is made possible by the generosity of his friends and family. He joined the faculty in 1909, became chair in 1927, dean of the graduate school in 1938, then he retired in 1946, and we're not done. He was president of the OSU Research Foundation, serving until 1958. He passed away in 1969 at the age of 72. Now tonight we are honored to have as our speaker the 2012 Nobel laureate in physics, Dr. David Wineland. Dr. Wineland was awarded the Nobel Prize in Physics along with French physicist Serge Haroche for groundbreaking experimental methods that enable measuring and manipulating individual quantum systems. These measurements constitute one of the first steps in building a new type of superfast computer based on quantum mechanics. Dr. Wineland got his undergraduate degree from the University of California at Berkeley in 1965 and a PhD in 1970 working with another very famous physicist, Norm Ramsey, at Harvard University. He's a member of the National Academy of Sciences, a fellow of the National Institute of Standards of Technology, and project leader there of the Ion Storage Group. In addition to the Nobel Prize, Dr. Wineland has also received many other national and international honors, including the National Medal of Science. Tonight, Dr. Wineland will speak to us on the topic of superposition, entanglement, and raising Schrödinger's cat. So please welcome Dr. David Wineland.
Thank you, Jim. Well, I think probably a lot of people are in the audience tonight, not because of the subject, but probably related to the prize. And I do want to say at the outset, and I think both Serge Haroche and I, who I shared the prize with, feel the same way. I think that, you know, although the prize in some ways, unfortunately, tends to represent just a couple of individuals, but I think we both feel that we're you know, that what the award is given for represents a large number of people working on a common theme, and as flattering and as nice as it is, I think we feel most that we're representing the field rather than individual accomplishment. So with that, let me get started here. This idea of Schrödinger's cat comes from Schrödinger, and he was, as one of the inventors of quantum mechanics, what I'm always impressed by was he, you know, it's been a fantastically successful theory, but he was dissatisfied right away and with the idea because, or the theory of quantum mechanics, because if you extrapolate it to our macroscopic world, I mean, it leads to some bizarre consequences, and his way of expressing that was his famous example where he posed this situation where, let's suppose you have a sealed box, and the idea that you know the inside doesn't interact with the outside world, but so the problem he posed was, in principle, of course it's impossible to write this, so complicated that you can't write down the equations, but in principle you could write down the quantum mechanical equations that describe the situation. And all quantum mechanics tells us is that if we start out in this system here, well, I should have said, there's a radioactive particle, and then there's some mechanism that if the particle decays, it releases poison and kills the cat. And you could, in principle, write down the equations, the quantum mechanical equations that describe this situation. And all quantum mechanics tells us is that after a time equal to the half-life of the radioactive particle, that all you can say is that the cat exists in some superposition being not alive or dead, but alive and dead at the same time. And so this bothered Schrödinger a lot, of course, and it's still, I think it bothers a lot of us today, but we can at least start to play in this world where we make superpositions like this. We don't do it with big objects like cats. But anyway, for the non-physicists out there, let me give you I think there's a nice analogy to superposition. And if you'll play along with this optical analog here. So if we have this box up here, you can, if you, at some instance of time, you might see this face be in the foreground or this face be in the foreground. So for example, you might tend to see one of these two images. And in some sense, this analog is very much like superposition in quantum mechanics. That is, there's an ambiguity about which state, you might say, the system is in, whether this side or that side is in the foreground. And when you're, when you look at this thing and your eyes tend to lock on one image or the other, that's very much like measurement in quantum mechanics. So this idea, this ambiguity is that in this case, the example of the box, it possesses both properties, these two things at the same time. And then when you tend to see it in one orientation or the other, that's very much like when we make measurements in quantum mechanics. We may be able to make these superposition states, but when we actually measure them, they jump into one condition or the other. And this idea of entanglement, I won't say a lot about this, but it's certainly part of the things we think about. And in this case, it's again superposition, but it's where, in this example of the boxes, it's where if you'll play along with the optical analog here, is that if I look at this box and I tend to see this square be in the foreground, like down here, I tend to see this other box be in the foreground as well. And it's this idea of entanglement, is that in superposition, is that when we create this state like this, that that the measurements we receive on the two systems are correlated in the sense, and in this simple example, as I said, when we tend to see this, at least for me, when I tend to see this face be in the foreground, I tend to see the other one be in the foreground as well. Oops, and the analogy, coming back briefly to Schrödinger's cat, this is actually, his example was one of these entangled superposition where there's this correlation between the two systems. If the particle is undecayed, then the cat is alive, and if the particle has decayed, then the cat is dead when we actually do the measurements. So this, as I say, that going back in history, the founding fathers, including Schrödinger, would discussing the consequences of quantum mechanics. These ideas, and what led Schrödinger to this apparent paradox, was that they tended to think about simple systems, and then when extrapolated up to the macroscopic world, it led to these strange consequences. So one way out of this, as late as 1952, Schrödinger said, well, maybe we're leading ourselves astray by thinking about these simple quantum systems. And so he said, well, we can never really experiment with one electron or atom or molecule in these thought experiments that the founding fathers would discuss. That, we assume they do, but this invariably entails ridiculous consequences, meaning extrapolated to the macroscopic world, we see things like Schrödinger's cat. And the problem with this, of course, is that nowadays we can enter this world where we can play with these simple systems, and we can realize these analogs to these systems that they were considering. And what we need for this is, it pervades all of physics. What we want is precise control of these quantum systems. We want to isolate them from the environment as well as we can. And we can't make Schrödinger cats or anything that big, but we can play these games with small systems. And in fact, I'll try to convince you later that we can make real analogs to Schrödinger's cat, even though they're small. So, what this lecture is going to be my personal story, and actually this is close to the lecture I gave with respect to the Nobel Prize. What they wanted us to do in these lectures was tell our story of why we were recognized. So this is certainly a personal story, but in the same breath, it's due to a lot of other people working on similar problems. So my story is the following. When I was a graduate student, I was in Norman Ramsey's group. And this is Norman Ramsey here. This is me just here trying to get close to the boss, you see. Anyway, so this was, when I joined this group, it was not very long after he and his close colleague Dan Kleppner, who I understand gave this lecture a couple of years ago, they had invented and demonstrated the first hydrogen masers, and this was a form of a way of doing high-resolution spectroscopy other than the application to atomic clocks. But anyway, after they had done these first demonstrations, Norman wanted to have an accurate measurement of all the hyperfine frequency that this maser is based on for all the hydrogen isotopes. So I chose the project of working on deuterium, and I like to say I think I'm the only one in the universe that has this number memorized, but it was the key result of my thesis is why I remember it. But anyway, certainly what this experience taught me was, first of all, I just like the idea of high-resolution spectroscopy, these very precise measurements from an aesthetic point of view. But more basically, what helped me through the rest of my career is it taught me how to think about making precise control of the environment. And also, at that time, we were maybe not thinking of it this way, but basically in these maser experiments, we create the superpositions of the excited state and the lower state that the maser works on. And in fact, these superpositions were actually fairly long-lived, on the order of a second. So then I went on for a postdoc position after graduate school. I went in to work in Hans Demold's lab at the University of Washington. And actually, I was first attracted. Hans had done experiments on high-resolution spectroscopy on atomic ions rather than neutral atoms, and I was attracted by that. But when I went there, he was most interested in experiments that towards measuring the magnetic moment of the electron. So the devices we use, we call them traps, but basically it's just an electrode configuration. We put potentials on these electrodes, and we can confine charged particles, in this case electrons. And so schematically, we think about some electrode structure, and when the electrons move back and forth in this, it's actually kind of like a harmonic well. You can think of the classical analog as a marble rolling back and forth in the bowl. But anyway, because the electrons are charged, we can look at them electrically, and it turns out, for those familiar with this, that there's an analog to or an equivalent circuit that these electrons inside this electrode structure, it's a tuned circuit. But again, what you can think about if you're not familiar with that, it's just like a marble in a bowl. And what we do is to isolate single electrons. The reason for that was, it turned out the goal was to do this precision measurement on the magnetic moment of the electron. And it turned out became clear that we could do the most precise measurements if we did it on single electrons. So that was the motivation here. Anyway, we could either, if you're familiar with a circuit analog, we could make a circuit like this where we would drive the electron. And what we did is that, or if we had a group of electrons, we would drive them in an oscillatory motion. And occasionally, in this analog, one of the electrons would just fall out over the edge of the bowl here. And in the electrical analog, what was happening is that occasionally one electron would strike the electrode and be absorbed and lost. And so this is the kind of data we would see. And so in this particular example, we started with 7 electrons and we adjusted the amplitude of this oscillation so that occasionally one of the electrons would fly out. And of course, the interesting case was when we got down to this last step, we would turn this off and then do experiments on the single electron. So one of the, as I mentioned, Hans Stamos was particularly interested in this measurement of the magnetic moment of the electron, and with his colleagues later on, they did this precision measurement, and this is largely why Hans Stamos got the Nobel Prize. It was actually in the same year that Norman Ramsey got the prize. But anyway, at that time, I was still thinking about spectroscopy, and Hans Stamos was too, and we had some ideas about laser cooling, and I won't take the time to describe laser cooling if you're not familiar with it. But anyway, it was an idea to use the radiation pressure from lasers to retard the motion of, it could be ions or neutral atoms. And so we had some ideas, and at the same time, Ted Hench and Art Schella had some ideas. And the reason, I mean, this has become a tool in a lot of atomic physics now, particularly for low temperature experiments. But one of the key things at that time that was interesting was that the cooling, the lowering of the temperature of the electrons suppresses time dilation shifts in spectroscopy. And for some of you, you may know the idea of the twin paradox that was posed by Einstein. The idea is if you have a twin brother or sister, and you could arrange in principal conditions where they go out on a fast-moving rocket ship that goes near the speed of light, and they could come back, and you can cook up situations where your twin brother or sister comes back and they've only aged a year, whereas you've aged 10 years. And that's a real effect that we have to worry about. Not only that dramatic example is certainly seen all the time in particle storage rings and things like that, but in our clocks, that actually occurs on a very small scale. But the clocks now, you'll see, are so precise that we do have to worry about these effects like time dilation, and so that's why this idea of laser cooling was important in the clock business. So after my postdoc position, I went to what's now called NIST, within the National Bureau of Standards, and my first job was to make the atomic clock based on cesium neutral atoms, which would fly through this long tube, and while they were traversing this tube, we would make measurements on their hyperfine frequency, and cesium is its so-called hyperfine frequency, which is a microwave transition, still provides, it's the definition of the second. So when 9 billion and so many cycles go by of this oscillation, that defines that's the accepted definition of the second. But anyway, at that time, my boss at that time, when I went to Bureau Standards, it was largely, at least the time and frequency division where this work was done, was largely more of a service organization. Our mission was to provide the unit of time, the second, through this device here, and also do calibrations. But my boss at that time was more forward-thinking, and fortunately, he was able to get some seed money for us to try this idea of laser cooling. So there was 2 experiments that first reported this laser cooling, and our competition was a group in Peter Toshek, then at Heidelberg, and actually Damelt had taken a sabbatical to go work with us. So one of the interesting parts of the story, you'll see that these first demonstrations were published in close proximity. Our paper was slightly ahead, but to be fair, if you notice the submission dates here, theirs was 1 day ahead, so I guess they're the winner here. But actually, what was actually really curious, this near coincidence was interesting, because I knew that they were working on this. I didn't really know where they were in the experiment, but I knew that because I knew Damelt had gone to work with them to try to do this laser cooling, and I'm certain they didn't know that we were even trying to do it. So it's actually an amazing coincidence, even though we had no knowledge of where the experiments were, that this was this near coincidence on reporting the work. And in the experiment of Peter Toshek, what they did is these first experiments were fairly crude. They could infer this cooling effect from the fact that they could hold ions in the for a longer time when the cooling was on versus when it was off. And in our case, taking what I had learned about the electrons, these induced currents that we were measuring, where you saw the steps in the electrons, here the idea is we looked at the induced currents, but they were just the thermal currents of the ions moving around inside this trap structure, and it was just the induced thermal noise that we were seeing. And so we could actually, that was proportional to temperature, so we could, at least at some level of precision, get a nice temperature measurement when we turned this laser cooling on. So anyway, this was the whole group after, not long after these first experiments reported. And the embarrassing part for someone like me is you can see these guys over here aged quite a bit. And actually, my colleagues here, Wayne Natano and Jim Berquist, they look pretty much the same, but some of us didn't fare so well. So one of the next interesting thing was that coming back to spectroscopy, it was just as in the electron experiments, it became clear that we could get the highest precisions, that is, control the environmental effects, best by going to single ions. So in some of the first experiments here, the group of Peter Toshek clearly beat us in this case. But anyway, both experiments were able to get down to single electrons. We again used this kind of step loss method. We were looking here at scattered light from the ions rather than the induced currents, but the results were basically the same. We could see the steps due to individual ions. What's interesting about the work on barium by Peter Toshek's group is that they could actually make photographs of individual ions. And what's interesting about barium, it's one of the few ions that fluoresces in the visible. Most of the ions, because you've removed one electron, they fluoresce in the ultraviolet, so you can't see them. But you can actually see a single barium ion with your eye with some small modification. If you look in one of these traps, it's kind of like a faint star, but you're actually looking at a single atom in that case. So in our experiments at NIST, a lot of this work, in fact, I have to apologize a little bit for the abstract of this talk. I had more focused on this idea of quantum computing, which I'll get to, but a lot of this spectroscopy work we did was a precursor to that. And so that's why I'm going to describe some of these experiments. So we chose to look at mercury ions in these single ion experiments. And one of the difficulties with mercury is we needed a fairly short wavelength continuous laser to do this cooling and observe the ions through their scattered light, the fluorescence. And this was the fellow I showed in the last view graph, Jim Berquist, is the one to develop this. This was kind of the record holder for a CW source for many years at this short wavelength. In any case, the idea is that what we, in an energy level picture, what we're doing when we shine this laser light on the ion is we're exciting it from a ground state to an excited state, and then when the atom decays, it emits light. And we look at this scattered radiation in these experiments to tell what's going on. Well, the reason we chose, here's a picture. This was just a still picture. And what we did in this, to give you an idea, you can kind of see the outlines of this upper electrode and with the inner part of this donut electrode, and in fact you can see a single ion. Now this had to be done with an ultraviolet video camera, but basically we can see single ions this way. Now the reason that mercury was interesting to us in this was because of the frequency standard application. And one thing we had our eye on was that mercury has another transition. So from the ground state, there's also this so-called D level, And the interesting thing about that, whereas this lifetime of this level here is just a few nanoseconds, the lifetime of this level here is about 1/10 of a second. And so what that means is that the frequencies over which this transition absorbs are extremely narrow range of frequencies, and this is what you want in a frequency standard. So let me give you the 30-second lesson on frequency standards. Is basically the idea is you in all atomic clocks, you make some oscillator that produces radiation at the oscillation frequency. You shine that radiation on an atom, and then and what you look for then is when this absorption process occurs with maximum probability. And when you reach this synchronization condition, what it means is that the radiation you're illuminating then with is oscillating at the same frequency as the oscillations of the electrons in this transition. Anyway, when you reach that condition, you have your standard, because then what you do to create units of time is you just count cycles of the oscillator that's producing the radiation. And in fact, in a nutshell, that's all there is to an atomic clock. That's how they all work. So anyway, this one was particularly interesting because of this very, very narrow transition. And so we started work on this in 1981, but it took us many years to get to the point where we could make a clock out of this. Anyway, the idea is the following. So when we do an atomic clock experiment, we first prepare the atoms or the ion in the lowest state. Then we apply this radiation, and then we want to tell whether the transition has been made. And the way we do it is simply as we look at the light from this other transition. So the idea is that if we're off resonance and the ion doesn't make the transition, then when we turn on this laser, we see the scattered light. On the other hand, if it's been promoted to this level, when we turn on this laser, then we don't see the scattered light. So we can see the state changes pretty clearly, and this is the kind of data we see. And so when the ion has been promoted to this state here, that basically the scattered light from the ion almost goes to zero. There's just some background light here, but we can clearly tell when the ion makes the transition. So this is a very nice way to detect these transitions in the ion. And just obviously we can't do a measurement. We have to repeat these measurements many times to get some statistics to tell when this laser is tuned to the right place. Anyway, so one of our projects has been this experiment on this optical transition, and Jim Berquist, who I mentioned before, has really led this over the years. And just a couple of points about this is that, first of all, there's many things we have to worry about that perturb the frequency, and a couple of these are observational effects. So the one we have to worry about is if just from the so-called first-order Doppler effect, which you are familiar with. When I was a kid, people would couch the example in terms of a train whistle, a train coming toward you, the pitch is higher when it's moving away. And this observational frequency shift is something we worry about. Well, one nice thing in these experiments, not only ions but neutral atoms, when we trap the ion, on average we know it's in one place, so the velocity goes to zero, and that cancels this, or essentially nulls this first-order Doppler shift. I mentioned the time dilation shift, and so laser cooling helps us with that. Some other little things is that we actually put this trap in a system at 4 Kelvin. The reason that was important was sort of a dirty effect that it turns out when we have we would make ions in this vacuum system by having a little bit of mercury vapor in the background, and it turns out that mercury, when it's in this excited D level up here, when it collides with a neutral mercury atom, it can what's called radiatively associate it. The electron will be de-excited, and then the ion will make a dimer, a diatomic molecule, basically, and that kills the clock, of course. So the reason we went to the low temperature was just to get very high vacuums. And sort of the interesting number is that in the experiments before, when we were operating at room temperature, the lifetime of the ion due to this process would only be about 10 minutes. And drive us crazy. It would take us that long to get things tuned up. And so when we went to 4 Kelvin, basically 4 Kelvin freezes out all the background gas, including mercury. So the lifetime literally went from 10 minutes to about 6 months. And we only lost those ions because we did something stupid, and otherwise they would have really lasted forever. Anyway, after a long, a long period, you see just from the date down here, after many experiments over the years, Jim led the work that finally reached the condition where the uncertainty, which we usually expressed fractionally, that it means the frequency uncertainty divided by the frequency is the relevant parameter. And we finally exceeded the performance of cesium in this experiment, where the fractional uncertainty was a little bit below part in 10 to the 16. And what's amazing to me is that in fact we're now in the position where these optical atomic clocks, and there's other examples, they can, it's clearly that they're better in terms of these controlling systematic effects than the cesium atom. But what's amazing to me is that the cesium atom was adopted as the standard. The first clocks were made in the 50s, and then the standard was adopted in the mid-60s. And it actually was the best clock until 2006, so it was an amazingly good choice. And now we're in the situation where even though these optical clocks are better, there's no obvious winner, so you don't want to just go change the definition of the second based on what happens to be the best in that day. And so it's not clear. My feeling is that the cesium will be the standard still for a very long time. And anyway, I've only talked about our experiments, but there's work going on in many other labs throughout the world, and these are some of the ions that are also investigated in this particular article I'm citing, because it summarizes a lot of this work going on in other labs. So one of the next things in this quest for control was to try to get down where we were controlling the individual quantum levels of motion. So again, in the classical picture, you can think of a marble rolling back and forth in the bowl. But we know when we go to the quantum level for this harmonic oscillator, in general for any harmonic oscillator, what we need to think about is, rather than some continuous picture that the energy of the oscillator could have, we need to think about in terms of quantized energy levels. So there's typically a ladder for harmonic oscillator, ladder of equally spaced states. And the one thing that makes it harder is in the energy separation here compared to the energy separation here is about 1 billion times higher. And so we're just, the energy separation here is much smaller, so we need much more delicate control to manipulate the quantum levels of the motion. And one way to think about when we probe this transition here, what I focused on before was the central feature, was what I was describing. But what you can think about in the classical picture, if the ion is oscillating back and forth in its trap, if you're sitting on the ion, what the laser looks like, it looks like it's frequency modulated due to the first order Doppler effect. So when we actually do this experiment, when the ion is at some finite temperature, we see these frequency modulation sidebands. Now the interesting part of this spectrum here is the central line, and what that represents the transition frequency here when the ion is at rest. And on the quantum picture, what that means is when we excite this transition, we're exciting from one motional quantum state to the same motional quantum state in the excited state, in the excited internal state, this D lobe. And when we think about these frequency modulation sidebands that are natural to think about in the classical picture, what these sidebands represent is, in this particular one, at the larger frequency, it represents the case when we make this internal state transition. We're also changing the emotional state quantum number by 1. And similarly for the lower sideband, what's happening here is we're exciting this transition, but at the same time decreasing the motional quantum number by 1. Well, how can we use this to get to the ground state? And actually, the idea is pretty simple, and but needs one ingredient. And this ingredient is the following: we can arrange conditions such that that is due to how strong they were trapping the particle. When the atom actually decays back to the ground internal state, it does so primarily without changing the motional state quantum number. And this is, for the physicists out there, this is basically an optical analog of the so-called Mossbauer effect. Well, anyway, if you followed a little bit what I was saying before, then the simple way we do the cooling is what we do is we tune the laser to this transition down here, where when we promote the ion up, its motional quantum number is reduced by 1. So when the atom decays, it primarily does so without changing the quantum number. And then what we do is we just leave this laser on for a little while, and eventually the ion works its way down the ladder of states, so it ends up being in this lowest state. And it's really not more complicated than that. There's a lot of technical things we have to worry about, but we're able to then get down into this lowest quantum state of motion. And in fact, so of course, if we leave that laser on that wants to reduce the quantum number by 1, of course, there's no state for the ion to go to so that scattering stops. And in fact, this provides a convenient way to tell us we're in the ground state. So what happens, these so-called sideband features on the spectrum, the lower one disappears simply because if we're in this lowest ground quantum state of motion, there's no transition to be made, and so this sideband disappears. We're not able to excite this transition, and this sideband that we see disappears. And in fact, we can then verify that at least on average, that the motion quantum number is very, very near 0. And I'll come back to this in a minute because it's sort of the basis also for quantum logic, the fact that we're not able to drive this transition when it's in the lowest state. So let me come back to Schrödinger's cat first. And so what we did in an early experiment, you can see this is around 1996, is that we made kind of an analog to Schrödinger's cat. So if you play along here, the idea is the following: we would first freeze out the motion, and then we would put the ion in its internal ground state. And I'm changing notation on you here, calling this, making the analogy to a spin 1.5 particle, where the lower state might be the spin down and the upper state spin up. So it's just a label. And then what we do is that we can, we first make a superposition. We shine radiation on this atom, so it's in a superposition of the ground and excited state, represented by these symbols over here. And then what we can do, again, a lot of details here. I can't go into the explanation, but it turns out we can make using what are called optical dipole forces, basically generated with lasers. We can apply a force to the ion, but in this particular case, we apply a force that only acts on the spin-up component of this wave function. And what that does then is we make this force, we modulate the force at the natural oscillation frequency. And what we can do is then we can start to excite the higher energy level component of this atom. So this part of the wave function starts to oscillate. And then just to make the situation a little more symmetrical, what we did then is we flipped the spin state. We changed. We went from ground to excited state and excited state to ground for these different components. And then we applied the same force again, maybe with a different phase. But in the end, what we ended up with was a situation here where at some instant of time, our atomic marble would be both on the left side of the bowl and the right side of the bowl correlated with its internal state. So in this notation, we use this is this situation I just described. And what we're saying is that this is very much like Schrödinger's cat. And if you'll play along here, the analogy is that with the analogy to the radioactive particle is the internal quantum state of the ion, and the more classical-like property is this more macroscopic motion of the ion oscillating back and forth in the bowl. And so, in fact, it's a very small version of Schrödinger's cat. That is the classical part in particular. So, in this particular experiment, this first experiment, we only reached the condition where the wave packets that describe the physical size of the ions was about 10 nanometers across, and we could only separate them by about 80 nanometers. And of course, you can always argue, and some people do. Well, you say this is too small to call it a Schrödinger cat. It's microscopic. And this comes back to what's still one of the fundamental problems in quantum mechanics. If you say this is too small, then where's the dividing line? And nobody's been able to come up with, where, if you could make the particles at some instant time separated by a centimeter, that's certainly more like Schrödinger's cat. It's a very macroscopic distance. And if you say there's a dividing line, you have to say where, and nobody can do this at this time. So this problem, in some sense, still remains. So anyway, about quantum information, in '95 there was a proposal by a computer theorist, Peter Shor, and in a nutshell, basically what he came up with is an algorithm that said if you could make a quantum computer, and I'll say a few words about that in a minute, that you could efficiently factorize large numbers. Now this sounds kind of esoteric, but I think many of you know basically all encryption, what secures your credit card and government secrets. The security is provided by the inability to factorize large numbers. And so basically, if you could make this quantum computer, it would compromise all coding that's done now. And anyway, part of the story is Arthur Eckert, who is already well known as some of these quantum ideas, particularly with respect to quantum communication. He came into an atomic physics conference that was held in '94 in Boulder. And basically, certainly most of atomic physics was unaware of this idea of Peter Shor's. Anyway, he told us about this. And anyway, I'll say a little bit more about how it comes to ions, but anyway, I'll give you an idea, just at least a flavor of why quantum computing might be interesting. So what I'll do is I'll compare throughout here how a classical computer works. So in a classical computer based on binary system, bits being zeros or ones, or in my notation earlier, spin down or spin up, the arrows pointing up or down. We know that the bits exist either as a zero or a one, but in the quantum systems where we can take say the energy levels in the mercury ion that I showed you, and we can label the ground state as zero and the excited state of one, we know we can make superpositions of the states. So in some sense, these quantum bits represent both a zero and a one at the same time. So one of the ways you can get an idea how this might be interesting is how it's scaled. So just take 3 bits. So a classical register can represent one binary number, say 101. But in this superposition sense, a state of 3 quantum bits can simultaneously represent all the numbers from 000 up to 111. Which is 2 to the 3, 2 to the number of bits. And for the people with some math background, you know that this represents exponential scaling. So a dramatic example is the following. If we had 300 bits in a classical memory, it could store maybe a line of text. In a quantum register composed of 2 to the 300 states, basically that's 10 to the 90 numbers represented at once, and 10 to the 90th is more than all the elementary particles in the universe. So in some sense, with this quantum memory, with 300 ions or quantum bits, we could store more memory than if you took all the matter in the universe. So that sounds pretty good. So one of the other things that's nice is it turns out in these algorithms, particularly in the factoring, which I can't, that takes many lectures to describe, but the idea is you plug in, if you're trying to factorize a number, you plug in from 0 up past the number you're trying to factorize. And when you do the quantum operations that I'll be briefly describe, it basically operates on all these numbers at once. So that even sounds even better, right? Well, there's one thing we have to remember, and what gets us is that in the world, we have to live by the rule of this. When we do the measurement, it's just like in Schrödinger's cat case, when we go in and measure, it's either going to be dead or alive, not dead and alive. In this quantum register idea, for example, even the 3-bit case, when we go in and measure the state, it's going to come out to be one of these numbers, say 101, with probability governed by the strength of these coefficients out front. So what that means is we have to be very clever in the algorithms that we design that use these quantum gates that I'll briefly describe. And in fact, Peter Shor's algorithm is one of these algorithms. And very briefly, what it's like, it's like a giant interference experiment. So all these quantum gate operations we supply are going to interfere all these amplitudes of these states. And in fact, for the people that had physics classes before, it's like the classic two-slit experiment where you pass light through the two slits, and downstream where there's an imaging screen, you tend to see, fringes. In other words, the light collects in one place and it's absent in other places. And anyway, so it's very much like that, but on a much more complicated scale. But anyway, let me just further give you an idea that there's some of these analogs. So in a classical computer, although it may not be the most efficient way, it turns out you can make a universal computer based on just 2 gates. So one of the so-called bit flip gate, and then an example that works is the 2-bit AND gate, which has this truth table here. And in the quantum world, we need to do something a little more sophisticated than this bit flip, is we also need to be able to invoke what we call more generally rotations, but an example is where if the bit starts in the lowest energy state, we can make a superposition of the lower and excited state. So we need to be able to do operations like that. And then the analogy, or an analogy with this AND gate, is what we call a controlled knot, and the truth table goes like this. So we call it a controlled knot because the state of the first bit controls what happens to the second bit. So in this example, if the first bit is in the one state, you can see it. The second bit flips either from 0 to 1 or 1 to 0. And anyway, so there's actually a pretty close analogy from what we call universal computation in a classical computer and quantum. And it just turns out that these operations, everything is just much more fragile with this quantum system, which is the challenge for us. So let me give you an idea of what we do with the ions. The 2 theorists that were at this meeting that I told you about in '94, these guys here, Ignacio Serac and Peter Zoller, are 2 well-known theorists in atomic physics, and in fact, they immediately jumped on this idea, and they were the first ones to actually make a comprehensive proposal for how a quantum computer might work. And so I can't go into the detail, but I can give you a flavor. So what they said was, well, okay, consider, say in this example here, we have 5 ions. And what you can think about this is like a pseudo-molecule. It has vibrations and so-called normal modes at different frequencies. And because they're at different frequencies, each one of these normal modes has a spectrum like the ladder I showed you for the single ion before. And what we can do is if we do this laser cooling to the ground state, what we can do is we can isolate the ground and first excited state of one of these modes of motion, and that we can have that act like a quantum bit. And the interesting part of this quantum bit is that the motion is shared amongst all the ions. So the simplest case to think about is the mode where they're all oscillating back and forth kind of locked together in the external potential that these electrodes provide. And so their idea was the following: if we could somehow, to make a gate between two ions, if we could somehow map the internal state superposition of this ion here onto this motional state superposition, and then if we could then follow that by doing a quantum gate between this motional qubit, which is again shared by all ions, and the internal state of this ion, then basically we've done a quantum gate between the internal state of this ion and this ion. And to complete the process, we actually reverse the first mapping step, and we put the motion back in the ground state and restore the initial state of the internal state of the first qubit. Well, anyway, I won't go through all the details, but I'll give you an idea of how the logic works in this simple example. And if we go back to the pictures I was drawing before when we talked about the cooling, the way we can get the idea of how the logic works is that if we tune our laser to the what we call the lower sideband, then if the motion is in this first excited state, that's the control bit, then we can turn the laser on for a certain amount of time so that the internal state makes a transition from the ground to excited state, given by these labels here. On the other hand, if the motion is in the ground state, there's no place for this ion to be excited to. So in fact, the truth table then is that is if the motion is the ground state, the bit stays the same. If it's in the first excited state, the bit flip happens. And the process to actually make a gate is a bit more complicated than this, but it's this conditional dynamics that we're able to realize that allows us to make these gates. And in fact, we were in a lucky position. We were starting to think about, before these ideas of quantum computing came along, we were thinking of processes like this. And so Chris Monroe, who was in our group from 92 to 2000, we were lucky. We were in the right place, so we could immediately jump on this idea. And we were able to demonstrate the key elements of this logic gate that Serac and Zoller had proposed literally within a month and a half. We got this thing going. So jumping over a lot of progress in between, I'll give you some examples of things that are going on, and these are certainly egocentric examples. I'm featuring two of my colleagues here, but anyway, we and a lot of other labs have done some simple algorithms that you might regard as subroutines in a larger quantum computation. So a lot of groups have done that. One of the interesting things is that this idea of quantum computing, especially to make a useful factoring machine where you want to factorize I don't know what it is, maybe a 300-digit decimal numbers. That's by far the hardest problem technically that anybody's thought of. So I think the short message is to make this factoring machine is way off in the distance. On the other hand, what a lot of atomic physicists are thinking about is that we can go back to an idea of Richard Feynman and others in the 80s, where what they talked about was having one quantum system be able to simulate another system. And one example of that in our ion experiments, this picture shows a different kind of traps where the ions are in a planar array. But what we can do is with these spin-dependent the state-dependent forces that I briefly described to make the Schrödinger cat, we can make oscillating dipoles, just classical. Well, they're at the quantum level, but the ions are oscillating back and forth, making dipoles, and we can make them depend on the internal states of the ions. And I'm glossing over a lot of details here, but these state-dependent oscillating dipoles, they can mimic certain systems that are of interest in condensed matter, for example, coupled spins in a lattice. So there's a lot of, I think what most physicists are excited about is even with a fairly modest sized system, maybe, somewhere between maybe 10 and 100 particles, we can actually do some simulations that are interesting from the condensed matter viewpoint. And I feature one of my strongest competitors, but also best friends over many years, and that's Rainer Blatt in Austria at the University of Innsbruck, and they've turned out, they've chosen the right system in terms of laser control, and they've been able to, at least on a simple scale, actually make a universal quantum computer on just a handful of qubits, but they've demonstrated the basic ideas of this, of building up a general quantum computer. And as I said, this is just a few examples and there's many more groups. And just to give you an idea, these are the groups that I know that are currently working on just the ideas of quantum information, quantum computing throughout the world. And you can see there's about close to 35 now. And this is just groups working on atomic ions. To give you an idea, the whole array of different physical implementations might be possible. There's ones based on neutral atoms. There's one that's gotten a lot of attention, that made a lot of progress in the last few years, is based on Josephson junctions, where they isolate two states that can be used as qubits. And so there's a huge number of groups working on this general problem throughout the world, not just with ions, but many other possible implementations. In the meantime, of course, our group has gotten a lot bigger now. This is our current group, and I won't have time to give proper credit to everybody here, but just to give you an idea of the size of the group. So let me just say a little bit about what goes on in the lab. What we might call our quantum computer occupies a tiny space over in a vacuum system in part of the lab. And as I mentioned earlier, at least in our case, these optical transitions are based on ultraviolet, and there's a lot of laserology that has to go into making these ultraviolet beams, and we need several of them. So our lives are dominated by making these lasers behave. And the other thing is, it turns out, just a little sidelight, is that I won't go into all details, but to get speed, what we want is the oscillation frequencies of the ions, these different modes, to be at the highest frequency attained. So the way we do that is, if for given potentials applied to these electrodes, we want to make the trap structures small. And so we've gradually worked the size of these systems down here. I haven't described this kind of ideal trap structure. It's kind of what we call a 4-rod quadrupole. And we can mimic this structure with devices like this. So we already got into lithographic techniques in these experiments, and some of our more recent experiments, we can actually make an electrode structure, excuse me, which is, in this case, where all the electrodes are actually in a plane, and the ions are suspended by electric fields just above this surface here. And in this particular example, each one of these little tiny squares represents a place where we can locate either one or a small number of ions. And what we're trying to do here is scale up to a much larger system by making these arrays. So that picture that I had the very first slide is the same picture of this electrode structure we're starting to play with. So in some sense, we're getting closer to what condensed matter experimentalists do by making these tiny structures, and maybe someday we'll kind of meet in the middle at some certain size. And in addition to our work here, there's a group, this kind of microfabrication is going on in a lot of places throughout the world. So let me come back to clocks, and part of the reason for that is, it's one of our main projects, and certainly been a main project ever since. So I've been at NIST now for 38 years, and it's been a theme that we've always done. So we've gradually tried to make these clocks better and better. Recently, we've been playing with an aluminum ion, which has an even longer excited state lifetime. And in fact, we could do the same thing we do with mercury. In principle, we could tell that when the ion makes the transition by looking at scattered light. Unfortunately, this scattered light we need a continuous source of radiation at this relatively short wavelength, and that's impractical right now. We can't get a source that does that. So what we do is we use some of the simple ideas of quantum information. So in this experiment, what we do is we have our clock ion, and then we have one of our ions that we use in these quantum information experiments, in this case magnesium. And if you remember back to this idea of Chirac and Zeller, where you first map the internal state of one ion onto the motion state, the grounded first excited state of motion, what we do is we do that process twice. So what we do is we first, after driving this transition, in general, the aluminum ion will be in the superposition, we map that onto the motional superposition of the ground and first excited state of motion. And then we reverse the process, map that into these states here. And in this case of magnesium, we can do this laser fluorescence method to read out the state of the magnesium, which means we're reading out the state of the ion. So let me, in these clock experiments, there's a whole host of things we have to worry about. I've talked already about this Doppler shift problem, and I cheated a little bit before I said that, the fact that we're holding the ion in one place with this trap, that the ion is not moving, so the average velocity goes to zero. Well, we're thinking of getting down to fractional precisions like this. What that corresponds to is a velocity of 0.3 nanometers per second, which is pretty small velocity. And in fact, what we have to do, the problem is that even though the ion is, to a good approximation, is located in one place in the trap, the laser is over on one side of the room and the ion is on the other side. And just thermal expansion, for example, gives velocities that are much larger than this. So we've had to take care of this problem for a long time. So what we actually do is we borrowed a technique from spacecraft ranging, and basically idea of the way you can measure the relative velocity of a spacecraft versus your station on Earth is you send up a signal, you essentially just reflect it off the satellite, and the signal coming back then has twice the Doppler effect, and you can measure that by beating that signal with the signal that's sent out. In any case, what we have to do is we have to stabilize the path length using this spacecraft ranging technique and get down to where we're much below a nanometer precision. I've mentioned the time dilation shift, which is taken care of to a large degree by laser cooling, but in fact this is still the limit. We don't quite get to the ground state, and this is what gives the biggest systematic effect right now. So we're down at this level here now with the aluminum, and actually I'm going to conclude with one other thing we have to worry about, and this also comes from Einstein, and this is the so-called gravitational potential redshift. So one of the consequences of Einstein's general theory of relativity is that he explained to us that clocks run at different rate, time runs at different rate in different gravitational potentials, and the size of this effect on Earth is such that for a height change of 10 centimeters, that gives a relative frequency, fractional frequency shift of about a part in 10 to the 17th, and I had mentioned we're down at this level here. And what this means in a practical sense for us is that nowadays it turns out when we measure two clocks, we have to be at the same location. And the reason for that is there's other ways to measure the gravitational potential, basically using little g gravity acceleration meters and doing a survey with these meters. But the problem, say for example in Boulder, where the mountains are, is that the uncertainty in the gravitational potential in Boulder is about plus or minus 30 centimeters. And what that means is if we want to compare to other clocks at some other location, these techniques that we use to remove the Doppler shifts, we can do that. But the problem is we're left with the uncertainty and the difference in the gravitational redshift potential. So, I mean, to me, it was really kind of disappointing that, after all my years working on clocks, all we're doing is measuring heights, But so we'll take the high road here, and the idea is to turn this around now and maybe use these accurate clocks in the future for geodesy. So let me give you an idea just for fun what we did in the lab to demonstrate this kind of on a human scale. So we called this one of our postdocs, James Chow. We have two of these aluminum clocks, and they're on fairly big tables, but we called this the portable clock because what we did is we put some jacks into this, and you can see what James here is doing is raising the table, and we were able to, we didn't do any, this isn't a precision measurement, but we were certainly able to see this gravitational potential redshift by moving the clock on the order of about 30 centimeters here. So I'm going to conclude. I'm sorry to run a little bit long. Let me conclude by saying, I've been really lucky in this. These guys that I started with, Jim Berquist and Wayne Otano and Bob Drollinger, and not long after that picture was taken, John Mollinger here joined us, and basically we've been working together for over 30 years. So it's really been a nice collaboration, in addition to, of course, all the students and postdocs we've had. More recently, Didi Leibfried has joined our group, and also Till Rosenben, who's, I didn't mention, but he leads this project on aluminum. Chris Monroe was an important part of the group for during the time he was with us. He's now at the University of Maryland, and of course, a huge part of the credit goes to all the students, postdocs, and visitors we had. And I've been lucky. And this has been a really nice place to work. I've been very supportive bosses, and our laboratory director, my boss's boss, one measure of her success is she's under her time as director, she's along with first Bill Phillips and then Carl Wyman and Jan Hall. I'm the fourth Nobel Prize winner under her directorship, and so she's been really just a great lab director. And of course, without saying, we've had to thank many agencies over the years for the support. And finally, let me say, I'm going to say a few words about the Nobel Prize ceremonies, which, the ceremonies are held in early December, and it's a very fancy thing. For myself, it's kind of a surreal experience. What I was saying to someone earlier this evening is it's such a big deal in Sweden, particularly in Stockholm. It gets a lot of attention, and when I would walk down the street, people would know who I was, because it's in the news all the time. Anyway, it's a very big deal. This was during the ceremony. Here's the royal family over here, and this was this year's Nobel laureates in the first row over here. Anyway, so it was as I say, kind of a surreal experiment. And anyway, after the ceremony in that evening, the king and queen invited a few people over for dinner. So this was the banquet in basically the city hall. And so one interesting thing to give you an idea how important it is in Sweden, not just to the laureates, is that basically, unfortunately, each laureate for these major functions was allowed to invite 12 guests to these functions. So there were 9 laureates this year. So with the guests, that's a little bit over 100 people. There were 1,200 people at this dinner, and basically, what the message, is that it's a big event for Swedish society and Swedish officials, and many of them are invited to this function. But nevertheless, it was a wonderful experience, and certainly something that won't happen to me, or meeting with the royal family in such a way. But and the other thing, what's been really nice for me, so Serge Hirosh, who I shared the award with this year, one of the nice things is I knew about his physics from very early on, and I got to know him personally about 25 years, and our wives have also become friends. So it was a real pleasure to be able to share with him. With that, I'll conclude. Thanks.
Thanks very much. We have time for a few questions.
I have a question. What did you eat at dinner?
The food was very fancy. What actually was one was kind of interesting. Every place we went, they wanted, to do the best for us. So a delicacy there is reindeer. So we actually had reindeer, a lot of reindeer, and we actually had some reindeer at the fancy banquet as well. But everything was very elegant, you can imagine.
Yes, next question.
Yeah, that's right. I mean, that's actually, certainly the military, you can imagine thinks of applications like that. Of course, it's not for small objects like you might find with your metal detector, but they're looking for, large densities or voids, you can imagine. So that's right, that's a potential application.
3 back from the previous questioner.
Yeah, in fact, there's no obvious winner for which ion we might choose. Some have different, advantages and disadvantages, and others will have different advantages and disadvantages. One I mentioned was in fact, what Rainer Blatt, my colleague in Innsbruck, they chose calcium, and it turns out it has the relevant optical transition is in the visible. And it was the right choice because all the optics are better. And one of the biggest problems we have is just controlling the laser beams at these ultraviolet wavelengths. So that was a big advantage in those experiments. So, but anyway, there's no clear winner. That calcium also has some disadvantages. But
Yes.
well,
Repeat the question.
The question is, can he speak about entanglement?
Well, it goes back to this, in this first few view graphs, and it's basically this idea of when you make these states, you get correlated outcomes, when the cat, the particle doesn't decay, and then the cat is alive. And what's interesting about these states, this also evolves from the early days of quantum mechanics. The idea is called the Einstein-Podolsky-Rosen paradox, and what it has to do with it, physicists are still entranced by this experiment. But let's suppose we forget the cat for a moment. But let's suppose we make an entangled state where we have 2 ions, let's say, and we make an entangled state where it's a superposition of them both being, say, in the up state, what I labeled with arrows, and the down state. And what's strange about this so-called APR state, and what's been shown is that if you make the state and then separate the 2 ions, what's interesting, or it's been demonstrated, fully with photons, but you can think about the ions here. But the idea is that when you measure this particle here, it's going to be you don't know what state it'll be in initially. It'll be either up or down. But once you know that it's, say, in the up state, then instantaneously you can show that the other ion is also in the up state and vice versa. And in fact, when you do this measurement, it's done somehow it's not really communication, but this collapse happens faster than the speed of light. That is, if information had to transfer between one place and the other, it does it faster than the speed of light. And there's various reasons why we can't use this for communication, but this effect that I just described is real. There's something that happens. What Einstein called this spooky action at a distance, that something which causes the collapse would actually go faster than the speed of light.
Yes. When did we see a quantum
Okay,
computer?
well, my standard answer is don't invest yet. and I think, first of all, I should say that, I mentioned that, I gave you all the wonderful properties of quantum computers, this parallel processing and all that, but, there is this caveat, that when you measure it collapses to one state. So we're not going to get rid of our normal computers, and in fact, it'll have a very specialized application. And I think, as I also mentioned, I think most of us think the real application is going to be in simulation, and partly because it's a simpler problem, it's still a hard problem, but not like this factoring machine. So I think, as I say, most of us are pretty optimistic that may happen. It may not happen in the next decade, but I could believe it might happen, that there'll be some problem that's solved with this simulator. So we'll see.
All right, well, I'd like to thank David again for coming and telling us a little bit about his work.